I'm happy to actually present my work on behalf of my students and my close collaborator, especially Jeremy Gunnison, who's in the audience, on our recent work on SkinnyPower, enabling batteryless wearable sensors via intra-body power transfer. So, supposed to work. Oh, there you go. So when we open up electronics, battery takes the most physical capacity. It's not only bulky, but it makes it very difficult to make flexible sensors such as e-tattoo or ergonomically designed sensors to be placed on very small parts of the body, such as on finger, inside your mouth, or in-ear fingers, in-ear sensors. And when we're talking about improvements of energy density over the past decades, we know that battery has shown the least improvement compared to any other components that comprises mobile devices such as CPU power, RAM sizes, and network speeds, and so on. Furthermore, when we are considering a future scenario in which we will wear a number of different sensors on our body to measure physical or physiological signals, especially with those wearable sensors with different battery capacity and thereby different charging time, it can be quite tedious to manage all the batteries, right? And last but not least, battery wastes have been starting to put a lot of impacts in our environment. So there has been a lot of effort to enable this wireless and batteryless wearable sensors. So for example, we can harvest energy from ultra high frequency signals such as cellular signals, Wi-Fi, or RFID signals. And then we've been seeing that we can harvest about a couple hundreds of microwatts. However, this is only operable under a infrastructure. And there always has been the curse of distance that you have to maintain a close proximity to the source of the electromagnetic signal in order to maintain a sufficient energy level. And because it's actually using the air channel, which is quite noisy, we know that the power transfer rate has been very inefficient. Solar energy, of course, has been used to harvest energy for wearable sensors as well in the form factor of wearable sensors, as well as more like a small garments that can be placed in part of the clothing. However, this requires a continuous exposure to the light sources, and it suffers from line of sight or occlusions from the clothing unless all of our clothing are equipped with such harvesting units. Our body can actually generate power. So for example, sweat can be used to harvest power. The friction between the body and the smart garments can be used to harvest power. Temperature differences between the skin and the environment also can be used, as well as the locomotion from piezoelectronic materials. And it has been quite successful to transmit milliwatts and watts of power. However, it again demands you to basically continuously walk or move your body or keep a certain temperature. And more so, even if we can, for example, harvest power in the shoe, the problem of transferring those power to different wearable sensors still remains as a challenge. So based on the fact that now we are quite used to charge different mobile and wearable devices, right, such as smartphones or wearable like smartwatches, we actually propose a different approach to solve the problem. Well, we're not entirely solving the problem, but we're basically introducing a new idea of enabling this wireless and batteryless wearable devices by transferring power from those batteries that we already have on our body, such as smartphones and smartwatches, to operate the batteryless sensors by transferring the power through the human body. So we're basically trying to use the human body as a power transfer medium from one device to another. So on the left side, we have an ultimate vision. We're not there yet, but we have a battery-powered smartphone in our pocket, which can actually power up different sensors at different locations of the body. In the middle, we have a smartwatch with a battery that can actually juice up the power to a batteryless sensor that is equipped in the finger. And hopefully we can harvest some sensor data such as accelerometer and then transmit that wirelessly. We also have a scenario in which, for example, we can have a Band-Aid, like a battery patch that you can put it on your shoulder, just like MC10, commercially available MC10 sensors and then provide power to sensors that are inside your ear or inside your mouth and so on. If this is in fact available, the key advantages is first, I'm going to soon talk about the frequency range, but the frequency range that we can operate on human body is much lower than the ultra-high frequency signals. So we're talking about a couple hundreds of megahertz of a range. Therefore, the generation of those signals is more power efficient. More importantly, the signal energy will be confined to or near to the human skin, and therefore is more efficient. And in the same line of arguments, because we are using the human body as a transfer medium, there's little interference and therefore lower attenuation compared to the air channel. And I'd like to actually highlight that we are actually trying not to compete with energy harvesting units, but rather I believe our technology can be more complementary to the existing harvest method, because we are focusing on transferring the power from one location to another. Okay, so in this work, actually, we have focused on this form factor where we have a battery-powered smartwatch, and then we're juicing up the power to operate a SoC, BLE SoC, with an accelerometer attached to it. So this is the applications. This was actually motivated an application scenario in which actually show that if we have accelerometer data on finger and the wrist, and if we can actually monitor their use of the hands, we can effectively track the recovery process of stroke survivors' use of upper limb in the real world setting. And more so, this ring type of sensors are becoming more ubiquitous. For example, in the market, so for example, Amazon just created this Echo Loop, which is in the pre-order phase as of now. Okay, so the main technical challenge is to secure the forward, which is a signal path, as well as the ground path. So in the left figure over there is conventional battery, and we all know that we need 2 wires to operate, or juice, take the juice out of it, which is basically the red line for the signal and black line for the ground. But our skin is one chunk of a conductive material which does not have that distinctive path. So we found a solution from capacitive coupling to establish this sort of a virtual return ground. Return path, and then this was actually inspired by the work in intra-body communication. So intra-body communication is using the body channel as a communication medium between 2 battery-powered devices. And it goes like this. So this is the power transmitter with on-body battery, and there is one electrode, conductive electrode that touches the body, or it needs to be it does not actually have to touch the body. It needs to be positioned near the body so that it can create a capacitive coupling to create the electromagnetic field, so that the signal can be actually flown through the human body. On the Batterless sensor, there's another electrode that are near to the human body as well. And then we have these 2 metal plates that are floating in the air. And when the signal is above certain frequency, say above 1 megahertz, it gets capacitively coupled to the environment, which creates a virtual ground path. So on the right-hand side is a simplified circuit diagram where we have a signal generator, or the power transmitter, and it uses the human body as a forward path, and then we create this virtual return path using capacitive coupling. Okay, so let's learn. So now we're injecting high frequency signal into our body. So let's learn about how body actually behaves as a transfer medium. So from 1 hertz to 100 hertz, the relative permittivity of the human body dominates the conductivity. So we cannot really efficiently push the signal through the human body. Between 100 hertz to 1 megahertz, the coupling becomes very weak to the environment. So the virtual return path is not effectively established. When the signal is actually above 300 megahertz, the wavelength of the signal becomes comparable to the human body, size of the human body, and therefore the human body starts to behave like a dipole antenna and starts to dissipate the energy into the air. So we're basically bound to this frequency range from 1 megahertz to 300 megahertz. So it works like a bandpass filter, basically. We specifically consider the safety regulation, and a section of our paper is dedicated to this. I'm not going to get into too much of a detail, but we follow the guidelines by the IC and IRP. Long story short, basically our system is much lower than what the regulation actually suggests. So it's completely safe. And it is not perceivable by the central nervous system, so we will not shock anybody using our system. Okay, so this is the system design of SkinnyPower, our device. Again, we have a battery-powered wrist-worn transmitter, signal transmitter. So first, this light gray represents battery. This dark gray represents electrode. So this is basically a wristband, and then inside where it touches the human skin, there's a copper, which acts like an electrode. And there's a green stuff over here represents the actual electronics, and the yellow block represents the ground plate that is floating in the air to make the capacitive coupling. And then, of course, it shoots the signal through the body, and the sensor node, batteryless sensor node, is actually exactly the same, but without the battery parts, right? And then we're creating this virtual return path through the environment. And we are actually collecting accelerometer data from the finger-worn sensor, and then we're transmitting data through BLE. So this is a design of our power transmitter, which is rather very simple system. So first we have a direct digital synthesizer, which is nothing more than a signal generator, which is operated by this microcontroller. And then the RF signal that is generated by DDS gets amplified using the RF amplifier. And then, of course, it goes to the electrode. So this is the copper electrodes that make a contact to the human skin. This is inside the wristband. And this is the ground plate that I talked about to make a capacitive coupling to the environment. And we actually used an off-the-shelf development board that was actually quite bulky. After the submission of the paper, we actually moved along and made this custom designed PCB board. This is also a prototype because you see a lot of white spaces, and we believe this can be further reduced in size. Okay, so receiver has two main components. First one is power harvester, and the other one is embedded sensor. So power harvester is basically composed of a copper electrode that receives the signal, which has been transmitted through the skin. And then we rectify the signal from AC to DC. Then we use a power manager which comprises of reconfigurable voltage booster and regulator. So we regulate the voltage. And we are, as we saw in the previous talks, we are also using the capacitor as an energy buffer. We use a 450 microfarad of capacitor. And we also have a supervisor to monitor the voltage level to enable this intermittent computing. Although we actually have not, we did not have the software, embedded software ready when we were actually building this, but we consider that as one of the design considerations. So this power buffer is actually used to operate both the SOC, BLE SOC, and accelerometer, and we are also monitoring the voltage level using one of the GPIOs. Okay, so this is our actual implementation. This is again custom designed. This is on the back side, you have the electrode again that touches the human body. We have a BLE SOC and the accelerometer on the other side. And this is the front side. And you see, we put a lot of vias and stuff for the debugging purposes, but this really can be small as the size of a fingernail. So, this is actually credit to Jeremy. This is Jeremy's arm. And we recruited 5 healthy individuals from the university, and it was quite bulky for our initial prototype, but now it's in the form factor of a wristband. So we actually investigated different important, say, parameters, the design parameters that are important for realizing this concept. The first was finding the optimal frequency. So I said that the frequency ranges from 1 megahertz to 300 megahertz. Unfortunately, we were able to go up to only 180 megahertz because the signal generator that we have only provided a sufficient voltage only up to 180 megahertz, although it was capable of going up to 300 megahertz, but we were not actually able to produce a very high frequency signal with a sufficient voltage. And we actually incremented the frequency by 20 megahertz. We asked subjects to straighten their hand and finger for 45 seconds. And the maximum average power was obtained at 100 megahertz right here. And we were able to harvest transfer about 800 microwatt of power. What's notable over here is that there is quite a bit of inter-subject variability. It means that human body channel behaves differently per different individuals. Which is actually corroborated by the S21 parameter, which also showed high variation when we used the vector network analyzer. Okay, so there were a bit of inter-subject variability, but in terms of intra-subject variability, it was quite reliable. So we repeat the same test 3 times over during the experimental period, apart by about 30 minutes, and we were actually seeing consistent performance. Although the sample size was very small, we actually ran the statistical test, but we didn't see much differences between the performance. So there goes the number. And we also investigated the distance between the transmitter and the power receiver. So we fixed the transmitter at the wrist, but then we moved the sensor from proximal to middle to distal. And then we asked subjects to basically straighten their hand. And we saw, we saw actually an inverse relationship between the distance and the power. So we start to see statistically significant drop when we actually move the sensor to 15 centimeter. We actually tested further apart. If you have questions about it, we can talk about it during the question section. But as per the results, this was what we have. And we also lifted. So I told you that the sensor does not have to physically touch the skin because we are using capacitive coupling between the electrodes to the skin as well. So actually we lifted up both the transmitter and the sensor from 0 to 3 millimeter by an increment of 1 millimeter. And of course there was an inverse relationship between the distance and the power that we can harvest at the battery at the sensor node. Basically we start to see a significant drop once we reach at about 3 millimeter. However, practically it's very difficult to actually, thinking about a wristband like smartwatch over here is very difficult to lift up everything by 3 millimeters. So we believe it's a practical solution towards motion artifacts. And also this means that when we actually have a power generator in the cell phone, even if it is placed in your pocket and there's a fabric between the sensor and the human body, can still inject power into our human body. We also tested different postures and body gestures. So we tested the straight hand, closed hand, wrist flexion and extension, palming, as well as arm swimming. And then we saw actually consistent performance throughout. So for the target application, which we wanted to measure accelerometer signal in the finger node, so we asked basically subjects to do any random movements using their fingers and hands, and then we sampled the accelerometer at 1 hertz and then transmitted over BLE. We used an advertisement mode where the packet was actually piggyback on the advertising packet. And we actually used the optoelectronic motion capture system as our ground truth label. So we placed the reflective markers on top of the accelerometer. And we manually synchronized the 2 systems. And in average, for the normalized error rate, we were achieving about 13%. So let me actually quickly show you the demo. So, this is actually sampling at 5 hertz. So we were able to increase, we continue working on this, and we were able to actually increase the sampling rate to 5 hertz. And then left is our sensing unit, right is our application that receives the data in real time. And we can see that we have another demo. So I don't know if you can actually see it. There's a LED blinking on the board. So you see the LED blinking over there? Can you guys see it? No? Yeah, sort of. Yeah, there's a LED blinking over there. There's no whatsoever battery on the receiver side. So there is actually a demo on Wednesday. My student will be actually presenting the demo, so please stop by to see this cool work. And a couple future work. First, we're providing power through the skin, but then we are using the noisy and inefficient air channel to transmit the data. So future work, obviously, we were trying to combine everything, both the communication and powering through the human skin. And more so, we believe we are capable of running multiple sensors from the single battery powered devices. So we definitely, but then, this is a big problem of intermittent computing that we need to be very careful about optimizing the power as well as, the performance as well. So this remains as an important future work. And that's about it. Thank you so much.